everyone. In the previous class, we discussed about the governing principle for the stress distribution for non-circular openings such as elliptical, ovaloidal, square and rectangular with rounded corners. And there we took three types of the stress conditions which were uniaxial, biaxial and hydrostatic state of stress. So today we will discuss how the stress distribution is going to be for multiple openings. As of now, we have discussed stress distribution or the displacement variation all around the boundary of any opening when you had a single opening. But then there can be the situation where you have more than one opening. Then in that case, how the stress distribution changes, let us try to take a look today. The stress distribution around an infinite row of equal size circular holes, that is what that we are going to consider. So right now we will focus only on the circular openings of equal size. And another condition which is going to be there, that these are equally spaced in an infinitely wide plate, and these are also subjected to either a uniform stress normal or parallel to the line of holes. Now the solution for such a problem was proposed by Howland in 1934, and here is the complete reference. So this problem corresponds to the row of circular tunnels having the same size and equally spaced in the horizontal direction at any given depth. That means the level at which the excavation is made for both the openings, or if you have more than two openings, it's going to be the same from the ground surface. So we are going to consider such a situation which is shown here in this figure. So you can see that we have the two openings, both are circular and are of same size, have the radius as small a, and its width is represented by WO. WO is width of the opening. Now you see that there is going to be an unexcavated space between these two circular openings, the width of which is represented by WP. This P is stands for pillar. So there is the unexcavated space and it will kind of form a pillar between the two circular openings. So the width of the opening is WO and width of the pillar is WP. Now another thing which you need to keep in mind is that the principal directions of the stress field before mining the opening or before excavating the opening, these are parallel and normal to the axes of the tunnels, with one principal direction being in the vertical direction. So you see that we have the axis as x-axis here as a horizontal one and y-axis as the vertical axis. So any point in the space will be represented by the coordinate r comma theta, r be the radial distance from this opening and theta be the inclination of this radial distance from the x-axis. Now the authors obtained the solution. We will not be going into the mathematical details of it, but we will directly try to study that how the stress distribution is going to be and how it compares with the situation when you had only the single opening which was circular in nature. So this is what is the stress concentration for a row of circular holes. So in this case, the opening to pillar width ratio is considered to be unity, that is W naught by WP, that is WO by WP is equal to unity when the applied stress field SY is normal to a line through the centers of the opening. So, in this case, the stress concentrations were plotted as a part of three variations. The first one, that is this variation A, which is written here, this is around the opening. That means that if you take the angle theta, here it is 0 degree, this is 30 degree, this is 60, and here it is 90. So, accordingly, the stress distribution was plotted and it looks like this. Then the second one is along the horizontal center line of the pillars. So this is what is the pillar. So the center line, so this is the horizontal line. So the variation along this is given by B. So this is what is sigma y upon SY. So everything, all the stress distribution we are plotting with respect to the stress concentration. And how did we define the stress concentration factor? That was the stress divided by the applied stress. So in this case, this is going to be sigma y upon SY, and you can see how the variation is somewhere here at the center line. It is approximately maybe 1.7 or so, and then it increases as you go beyond the center line. Then the third one is along the vertical center line of the pillar. So this is the width of the pillar and you draw the vertical center line, so which is this, and see how the variation looks like as you go in the vertical direction. So it starts from here at the center line, and then when you go move in the vertical direction, see how it changes, and when it is y by a becomes approximately equal to 3, this stress concentration is close to 1. So here this is the stress concentration with respect to the vertical center line of the pillars, that is sigma y by SY here, this variation. Now, if I just compare the case of a single circular opening with that of the two circular opening, take a look. This figure you are aware, we discussed it in some of our earlier classes. So you see that if I just take this at the boundary or theta equal to 0 degree, it was coming out to be 3. In case of the uniaxial state of stress, and you remember I mentioned to you that at the crown portion it is going to be critical because of the presence of this tensile stress situation. So the similar thing what we get here is at theta equal to 0, what we get here is as 3.24. Now, this is owing to the presence of the adjacent hole. So, the stress concentration factor, it increases from 3 to 3.24 in case if you have two circular openings. Now, this increase in the stress concentration is relatively quite small, considering the fact that the average stress on the line of centers of the hole is approximately twice that of a single hole in an infinite small plate. So, you see that although the average stress has increased twice on the line of centers of the hole, but then the increase in the stress concentration is relatively quite small, and therefore we can infer that the average stress in the pillar, it increases more rapidly than the maximum stress, and that the average stress in the pillar will approach the maximum stress as the ratio WO by WP increases. So please keep this in mind. Now, we have seen this that in case of the single circular opening, the stress concentration at R equal to 3A was found to be 1.074, and at 5A it was 1.022. This you can refer to one of our earlier lecture where we discussed about the single circular opening. So these values have been picked from there only. So therefore, the applied stress field at the edge of any one of the opening is going to be about 9.6% larger because of the presence of two adjacent opening. But at the center of the opening, what will happen? That is when you have R is equal to 4A. So in that case, for the adjacent opening and the stress field, it will be increased only by 1.074. Now the presence of the other openings in the row, they can have only the minor effect, and therefore the increase in the maximum stress concentration should be greater than 7.4% and not be greater than 9.6%. That means it should be somewhere in between 7.4 and 9.6%, and the result which we saw, that is 8.7% more than the maximum stress concentration for a single circular hole. So remember that it has to be greater than 7.4% and less than 9.6%. Now, in case if we have the opening to pillar width ratio, that is WO by WP equal to unity, and when the applied stress field is parallel to the center line of infinite row of circular opening. So in this case here, it is the Sx which is present. In earlier case, it was Sy which was present. So the stress concentration were drawn around the opening, above the opening, then along the vertical axis of the pillar and along the horizontal center line of the pillar. So let us take a look when it is around the opening. It is this figure, and see how it is changing. Like at 0, it is somewhere between 0 and minus 0.5, and at theta equal to 90, it is somewhat greater than 2. When you have this stress concentration curve B, which is above the opening, so there you see that it is just above the opening here, and what you have is sigma theta upon Sx here. So in that case, see, just at the crown you have this as 2, and then here it is 2.5, as you have this variation of R by A. Then along the vertical axis of the pillar, that is here, this one, vertical axis of the pillar is this. So this is the variation is Y by A. So here it is varying as 1, 2 and then 3. This is 0. So this variation, it starts from here and it becomes, or it follows this particular path. D is the stress concentration along the horizontal center line of the pillar, and which you can see that it is starting from R by A equal to 1 to it is going up to 2, and the variation sigma R upon Sy, which is on this axis, has been shown by this particular plot. So this is between 0 and 0.4. So in this case, if again I compare it with the case of a single circular hole, so in the single case it was 3 at the boundary at theta equal to 0 degree. However, in this case it is 2.16. Why are we considering? Because you see that in this case it was Sy, but when you have the Sx or in the absence of Sy is equal to 0, and if only Sx will be there, because it is symmetric, so you are going to get the similar stress concentration factor. So in this case here we are getting 2.16, that is at theta will be equal to 90 degree. So here whatever was there at theta equal to 0, the same will correspond to theta equal to 90 in such type of loading condition, because in this case it is Sx which is applied. So this reduction is the result of the shielding effect of the adjacent holes in the row. Now this shielding effect is even more pronounced on the horizontal stress sigma x along the vertical axis through the pillar, which is this curve, and the horizontal stress sigma r along the horizontal center line, which is this D. So focus on these two. You see that the maximum radial stress, you focus on this curve D, the maximum radial stress sigma r, it never exceeds 0.14 times Sx. You see that here it is sigma r upon Sx is given. So the maximum radial stress, it is 0.14 Sx. Now, if we compare the curves B and C and curve C of these two figures, where in one case you have Sy and in another case you have Sx, that is the loading condition, loading direction is different in both the situation. So, the zone of influence in which the stress distribution is altered uh, appreciably from the applied stress field, it extends only one diameter on either side of the center line of the opening. So you just take a look here, B, C and the curve C here. Okay, so you can just take a look that in either of the condition, wherever there is a change in the stress distribution, it is only up to one diameter on either side of the center line of the opening. So kindly keep this in mind. Now the stress concentration for biaxial stress field, as of now we discussed when Sy is present, and in this case when Sx is present. In case if you have the biaxial stress field, that means both Sx and Sy, they are present, and say for example that if these two are equal, then what we can do is these stress concentration factors, they can be given by the curves A, that is the curve A in this case and curve A in this case. So what we will do is, because we are talking about the elastic ground condition, and therefore the principle of superposition will be holding good in this case. So if you just try to combine these two, then in that case you will be able to get the stress concentration for an applied stress field which is biaxial. Take a look how it looks like. So you see that we have the row of circular holes, that means two we are considering here. This is the first one and this is the second one. We are considering only 1/4 of these holes. Now this results, they are for WO by WP to be equal to unity, and we are considering biaxial stress field with the condition that Sx is equal to Sy. So as I mentioned, just superimpose these curves. So you see this is how it looks like. So this was the curve which is for Sy equal to 0 and Sx not equal to 0. This is the curve where Sx is equal to 0 and Sy not equal to 0. This is the curve when you have Sx is equal to Sy, and this is the curve when you have Sx is equal to 1 by 3 of Sy. So you just simple superposition and you will be able to get the stress distribution corresponding to the biaxial state of stress. Now, the solution to the problem of two equal circular holes in a plate subjected to biaxial stress field was directly solved by this author without superposition in 1948, and the uh, details of this has been picked from this journal paper. So here you see how the geometry looks like. So you have the two circular openings with the radius b, and any point in the space is again represented by r comma theta, where theta is measured in the anti-clockwise direction from the x-axis. And note here that the origin is at the center of the pillar. Width of the opening is WO and width of the pillar is WP. And here it is subjected to biaxial state of stress, where it is Sx in x direction and Sy in y direction. So this problem was solved directly for the biaxial state of stress. So this problem corresponded to the two horizontal circular tunnels, and it was observed that the maximum stress concentrations, they occur at 2 points on the boundary of the openings. What are those 2 points? So in case if you have the uniform biaxial stress field, what do we mean by this mathematically is that Sx is equal to Sy and both are non-zero. Or for an uniaxial stress field which is normal to the center line of the hole, that means normal to the center line of the hole means that there is going to be the y component of the stress but not the s component of the stress. So that mathematically shows that Sy not equal to 0 and Sx equal to 0, and then the location that you will have is theta equal to 0 and theta equal to pi. Pi is 180 degree. Now, in case of the second situation for an applied stress field parallel to the line of center, that means here Sx is non-zero and Sy equal to 0. These maximum stress concentration will be occurring on the boundary at theta equal to plus minus pi by 2. Now, the maximum stress concentration for two circular holes in a plate, again these values has been picked from this reference only. So, you see that when the pillar to opening width ratio changes from 0 to 10, how the various stress concentration, they change for different loading condition. So the first column tells us about the biaxial state of stress, in which situation Sx and Sy both are equal and non-zero, while the second column gives you the idea about the stress field when there is the stress applied in only the y direction and not in x direction, and the third one represents the values of maximum stress concentration factor when you have the stress field only in x direction and not in y direction. So we have the variation at theta equal to 0 and pi for these two situations, as I mentioned with reference to the previous slide, and here in this case it is theta equal to plus minus pi by 2. And you see how the maximum stress concentration for two circular holes in a plate, they vary as the pillar width to opening width ratio increases from 0 to 10. See, at theta equal to 0 for the first situation biaxial state of stress, this is varying from 2.894 to 2, and at 180 degree it is varying from 0 to 2. Similarly, in case if you have Sy non-zero and Sx equal to 0, that means it is uniaxial state of stress. So again here these are the 2 points where you are going to have the maximum stress concentration, that is at theta equal to 0 and theta equal to 180 degree, and this is how the variation will look like. And in case you have the stress applied in x direction and not in y direction, in that case the maximum stress concentration is going to be at theta equal to plus minus 90 degree, and it varies from 2.569 and increases to 3. So this is how we can find out the stress distribution directly by the method that was given by Ling in 1948, where he solved directly these problems subjected to biaxial state of stress. Now, if you compare the results of both of these authors at Wp by W naught to be equal to 1, the stress concentration resulting from the two holes is considerably less than the resulting from the infinite row of holes. So kindly keep this in mind, that in case if you have the two holes and if you have the infinite row of holes, there is going to be the difference in the result. Now there are few things which you need to keep in mind, that the stress in the pillar side of the opening, it increases towards infinity as the pillar width reduces. That means when this Wp reduces, then this condition is satisfied, and therefore the small ratios of width of the pillar to width of the opening, it should be avoided in the underground structures. So this has the reference with respect to the stress concentration at various locations. So when you go for the underground structures where you have the multiple openings, so you should always keep that in mind, that you should avoid small ratio of Wp by W. So this is how you can deal with the multiple opening. So we discussed today about the multiple openings having circular shape. As far as this course is concerned, other shapes of the opening is beyond the scope. However, there are many numerical studies which are available which handles the non-circular shapes as well. So this is what was all about the multiple openings and their stress distribution. So in the next class, we will start our discussion on a new topic, that is opening in laminated rocks. Thank you very much.